Students, today our topic of discussion is the hybrid parameter of bipolar junction transistors. For this, let us suppose the transistor proper biasing circuit is inside that black box, this one, and we have two ports, that is, one is the input port, this is input port, and this is output port. So input port, there is an input battery and there is input current II, and at the output port there is output generated voltage VO and the output current IO, and you can see the input current is entering the system and output current is also entering the system, and this is because the fact that we want to make some positive signs here, and for this, according to the Kirchhoff current law, the currents when entering to a point, then it is positive. So keeping all these things positive, that sign convention has been taken, but in the actual problem the sign will come out with the actual sign. Now here we move on to this assumption. That is not assumption actually, because we have already read about the input characteristic and output characteristic, where in the input characteristic, in the CV mode or CE mode or the CC mode, you always plot the input voltage here and input current here, keeping output voltage constant. And for output characteristic, you have plotted the voltage versus current, that is output current versus output voltage, but keeping input current as constant. So here now we make the functional forms of the input voltage as a function of input current and output voltage from this curve, input characteristic, and the output current as a function of the input current and the output voltage from the output characteristic. So that is why it is hybrid. In the preceding section, you can be familiar with the term the hybrid parameter. So the functional relationship we have assumed here as linear. So VI is equal to some coefficient into I plus some coefficient into VO, and similarly IO is written, and you can see those coefficients are written as H11, H12, H21, H22 in the sense that it can be written in the simultaneous linear equation, so they can be written in the matrix form. So the symbols are here written in the matrix terminology, that is H11, H12, H21 and H22, where the here is II and VO. So it is written like this. So the meaning of these symbols, those coefficients, those 4 H parameters are justified. And now we are going to first define those coefficients. What are the meaning of such coefficients, those 4 coefficients? So if I suggest you that H11, what is that? You can put VO is equal to 0, then automatically first equation will give you VI is equal to H11 into II. So H11, forget about this, sorry, this one. Now H11 can be written as VI by II when you have put VO is equal to 0. So VO is equal to 0, that is output voltage is equal to 0, then the input voltage versus divided by input current is your H11 parameter. So H11 parameter is a resistance, because it is the ratio of the voltage and the current, but the resistance when the output terminal is short circuited, because VO is 0 means the output terminal is short circuited. Why? Because you can see VO is the potential difference between 2 points, this one and this one. If they are short circuited, that is a wire is connected between them, then 2 points will be of same potential and then VO should be 0. So VO is equal to any potential is potential difference is 0 means those 2 points are short circuited, and current is 0 means though that point is cut, that is open circuited. If I open this point, that is if we disconnect this point or cut with a scissor, then no current will flow, that is IO will be 0. So current is equal to any current is equal to 0 means open circuit, and any potential difference 0 means short circuit. Okay, short circuit. So this will be kept in your mind while defining those H11. So H11 is the input resistance or input impedance in general, you can say, because those Vi and Ii can be of time dependent in character. So these are input impedance. Why input? Because it is a ratio between input voltage and input current. Input impedance when the output terminal is short circuited to AC actually. So those quantities are defined as HI. H11 is defined as HI. Similarly, you can define H12, which is HR, that is reverse voltage transfer ratio. Actually H12 is what? It is H12. Yes, H12 means HR. So it is wrongly written here. It should be V0. Okay, it is wrong. Vi by V0 should be there when II is equal to 0, that is input current is 0, that means input is open circuited, and this term Vi by Vo, it is not the voltage gain, it is the reverse voltage gain, or you can say the reverse voltage transfer ratio. So that is why HR is written. Similarly, H21 will be I0 by II, that is output when V0 is 0, so output is short circuited. It is obvious, I am not again telling you that, it is understood, but I0 by II is the current transfer ratio or forward current transfer ratio or forward current gain, because output by input is there. So these two terms are actually dimensionless. First one is of dimension of ohm, that is impedance, and the last one is I0 by V0. It is actually a dimension of admittance when the output input is open circuited. II is equal to 0. So it is output admittance. So we have two equations, and now those two equations can be thought of that this one is actually looks like a KVL equation, and this equation looks like a KCL equations. This current is divided into two currents, and this voltage is divided into two voltages. So these are nothing but KVL and KCL equations. So we can imply those two equations into a model or into a circuit, which circuit is called the hybrid parameter circuit, and this can be, yes, this equation again it is written here correctly. So we can make this circuit. Why? First think about this section, the input section, this one. How does this section or this model comes? Now this model comes from the KVL equation, where this is your input voltage. Okay, so input voltage is equal to sum of the voltage drop at there and the EMF of this, or you can think that this is a voltage drop HR into V0, because HR has no dimension, so HR into V0 is another potential drop. the symbols are here. At this point, the bottom line is the ground point. That is, with respect to this point, all the potentials are measured. So you can see here Vi is obviously, you can go to the KVL formula and you can reach about this equation. II into Hi is the potential drop across this admittance impedance, plus this potential drop HR into V0, which is nothing but the first equation. Similarly, I0 is flowing into this direction, because actually black box part, you can think that the black box part is what? The black box part is starting from here. The black box part is starting from here and ending at this point. So that black box, outside the black box, the current is entering, and the current is I0. So I0 is divided into two parts, one along this direction and another along this direction, which is the current source, HF into II, because HF has no dimension. So HF into II is another current, and you can say this is a current source. So I0, according to KCL, you can write HF into II plus, as H0 is the admittance, so admittance into voltage is the current. So this is the equation of second. You can see above it is written, yes, this one. So those two equations are implemented in same circuit with a common ground. It is ground point. It is the ground point, that is zero potential, and this model is called hybrid model. Why hybrid? Because those coefficients Hi, Hr, Hf, H0 are not same dimensions. That is why hybrid. Hi has the dimension of impedance, Ho has the dimension of admittance, that is inverse of the impedance, Hr dimensionless, Hf dimensionless. So the H parameters, and you can read about the benefits or advantages of the H parameters, because it simplifies the circuit, the main feature of this. And another criteria of H parameter is that it real numbers at audio frequencies. Audio frequency means omegas are very low, so the terms admittance, admittance is there, but impedance is replaced by actual resistance. Those terms are all real for audio frequency, and our syllabus is concentrated to the audio frequency amplifier. So all the terms, all the coefficients will be real in our case. The most important study of the H parameter is about the CE configuration, because CE configuration, CE mode is used for the actual amplification purpose. So H parameter model of the C configuration should be we should be interested on. So the C model, again it is drawn here. RC is the collector resistance, and across which the output voltage is taken, and VCC is the DC. All the DC batteries which are connected here, you can see all the DC batteries actually should be zero when you are talking about the hybrid model, because hybrid model is actually the AC model. When the AC signal is connected, the hybrid model comes into play. So with respect to AC, the all DC batteries should be short circuited, that is no DC batteries are there. It should be kept in your mind. The DC parts, that is VCC battery or the resistances, and the self biasing circuit, it is not shown here. We have discussed in our previous class that a proper biasing is needed. So fixed bias or the efficient bias is the self bias or emitter bias. That biasing circuits are there, and after biasing, just think about that biasing circuit as a black box, and we are going to just calculate the gain, voltage gain or the current gain from the outside of that black box. we don't bother about the biasing, what is the quality of or the characteristic of the biasing, that is inside the black box. So all things are inside, and here we are just actually macroscopically we are calculating those things. Now for the CE mode, if the hybrid parameter model is drawn, then HIE should be written as HIE should be written as HIE, HRE, HFE and HOE. This E symbols comes from the common emitter mode. Okay, so this suffix is added with all the hybrid parameters, but the definitions are the same, exactly same. And here you can see in place of VO it is written VC. Actually VCE or E actually common, so VBE in place of VBE it is written simply VB, in place of VC it is written simply VC. So these are the terminologies which I have used already in describing the hybrid model, but here some extra symbols are added, and the corresponding VI is replaced by the actual potential, VO is replaced by the actual potential, and similarly for the input current and output current, those symbols are written. Similarly you can write all the modes using all the circuits, that is CEC, BCC, all the equations, all the KVL and KCL equations can be written with respect to the corresponding connections, that is whether it is a common emitter, common base or common collector. And typical H parameter values, all the values are written here for all the connections, and HI you can see it is very large for the input impedance or the input resistance is very high for CE and CC mode, and output admittance is very much low for CB. So those are things you can check from this this table. These are typical values. Now what is very much important is to study the H parameter model of CE mode and calculating the gains. Now connect the actual input AC signal which is operating in the audio frequency range, that is very low frequency range it is operating, and it has the internal VS is the amplitude of the input AC signal, and RS is the input resistance of the input signal, and IL is the current, or ZL you can see here. ZL is the load resistance through which the output voltage V2 is measured, and IL is the current. So V2 is equal to, simply you can see IL into ZL, or in place of ZL you can write RL, that is resistance, but in general studies it is written ZL, that is impedance. So yes, the hybrid parameter model should be like that, because this part is without any battery connection. So this part is coming from the black box, but the outside the black box the new AC signal has been connected and the output load is connected. So those two are extra factors which are added on to the H parameter circuit. Now let us calculate actually the current gain first. AI, current gain means the output current and ratio of input current. So IL by I1, and now we can see IL is what? IL is the load current flowing into this direction, and I2 is the actual output current. So IL and I2 are the same but with negative sign, because it is flowing in the same loop. I2 is flowing here and IL is flowing here, so they should be equal because there is no resistance or any other parameter, that is inductance or capacitors in between them. So this is a single path or single wire, so those two currents are actually same but in opposite sense. It is written over here because of some mathematical benefits. So in place of IL you can write minus I2. So we should find out first I2 by I1. Now from the circuit, I2 is this one and V2 is, I have already written, IL into ZL, that means minus I2 into ZL. So in place of V2 you can replace this one, replace equation 2 into this, and then by some either you can find out I2 by I1 like this. So I2 by I1, so negative, take the negative of that, the current gain should be minus HF by this one. These are all constants. These parameters can be evaluated experimentally, and some typical values are given in the above table which I have shown already. So this current gain is constant for a particular connection, for a particular transistor, in a particular mode. You can see here the different modes, then HFE and HOE or HFB or HOB will be written here. So this is the formula. And next, the input impedance. What is the input impedance? Input impedance means net input voltage by net input current, so V1 by I1. Now V1 you can find from the above figure, that is the KVL equation, this one. So Z1 is this, so I1. Now you have to find only this thing, V2 by I1. Process is same. From the expression of V2 you can find simply V2 by I1 is equal to AI into ZL. So put it down into the equation 1. So it will be looking like this, and you know the expression for AI we have already calculated it. Just put it down, this equation. See, when I am doing this, I am not writing here HFE or HOE because it is actually the mode independent study. Those formulas are equally applicable for all the mode, whether it is CE, CB or CC. So it is very much general study. So the symbols are simple, HF, HO, HI or HR. Okay. Now you can see the final expression is this. Similarly, you can find the voltage gain AV, which is V2 by V1, that is net, actually not net, the output voltage by input voltage. So following the same procedure you can find this. This is nothing new. Similarly, output admittance means I2 by V2, this should be calculated, and you can again get some constant values. And now the overall voltage gain, it is sometime called the overall voltage gain, because actual voltage is given by you is not V1. Actual input voltage is given by you is the Vs, which is the source voltage. You have spent your money to the source voltage and you will get the output voltage V2. It is fine, you will get the voltage output V2, but you have spent your money in the Vs. So Vs is the actual input voltage, not V1. So in place of V1 you put it, so actual voltage gain or the overall voltage gain is the AVS, which is V2 by Vs. Now we know V2 by V1, so V2 by V1 into V2 V1 by Vs. Now because this one is AV, which we have already calculated, the formula of AV we know, so AV is there, but V1 by Vs, yes, you can also calculate this from this diagram. This is the input section of the hybrid model. Here the RS and Zi is the input admittance, input impedance, which we have calculated already. So forget about the right hand side circuit, just input impedance is there. Input impedance means the circuit is offering some resistance or the impedance at the input port. That impedance is input impedance, and we have calculated already. Zi we have calculated like V1 by I1. We have the formula of Zi. So Zi is known to us, and we will going to exploit this because Vs, Rs and Zi is involved here, and V1 is the input voltage at the input stage of the hybrid model. So the relation of V1 and Vs is simple because V1 is the voltage divider circuit. So V1 is the total voltage Vs into Z1 by Rs plus Zi. So this is coming from the voltage divider circuit. From the series connection you can find this V1 voltage. Now V1 by Vs is this, and just put it down here. So AVS, the overall voltage gain which you will get from the circuit, is Zi by this. So here you can draw physical significance. If an amplifier is such that Zi is infinitive, then AVS will be AV by 1 plus Rs by Zi. So that should be equal to AV. So maximum voltage gain is AV. Otherwise, if Zi is not equal to infinity or not very high value, so the overall voltage gain should be lesser than the open circuit voltage gain, that is AV. Okay, so for a faithful amplifier or for a efficient amplifier, the input impedance should be made very large so that we can make use of the circuit as much as possible. Okay, it is written here. Or you can make Rs is equal to 0 also, but Rs is equal to 0 is not the physical thing because any battery can have should have internal resistance. So this can be also formulated from here. Similarly, the overall current amplification term also be different from AI. Okay, so similarly you can calculate this, but here you should consider the Norton equivalent circuit of the input in place of Vs. See, Vs and Rs are in series, but its Norton equivalent is Is current source and Rs as the parallel. So same input terminal is drawn, but with Vs as replaced as Is current source. So nothing new, the same calculation will follow. And this one are the particular cases for the C, CB or CC modes, and these are nothing else. And these are the conversion formula used for the hybrid parameters. If you know actually common emitter mode is the most general case, because if you know the common emitter parameters, that is H, IE you know, HRE you know, or HOE or HFE, all are known, then the common base or the common collector connection with that transistor, that particular transistor or that particular set of biasing components, you should not again calculate it, because there are some relations between common base and common emitter, and again common collector and common emitter. So common emitter is the main thing. If you calculated the common emitter parameters, then you automatically get the common base or common collector parameters using those relations, and those relations should be remembered. Those are not expected to be derived here. So the characteristics of all the common emitter or the common base or the common collector amplifiers are written here. You can just go through this, and these are very simple, which we have done here, calculating things. Those are actually summarized here, and you can see those terms are very much familiar to you. Just go through this and you can understand very easily. And there are some applications of those common emitter, common collector or common base configurations, and comparisons are there. You can see all the quantities can be found out experimentally. I have already said those terms, what are the values you can get from this table. See the common emitter, why I have always supported the common emitter, because it has high voltage gain and also the high current gain. Also you can see CB has also that, but the input resistance of the CB is low, but input resistance of the common emitter is high, and because of that fact you can make use of this gain fully. Okay, and the output resistance is very high, and but here output resistance is very low, so this is very much faithful towards the amplification, the common emitter mode. Now the last topic of our discussion is the hybrid model of common emitter mode, but with approximate analysis. Here we are going to draw the approximate connections. Approximate connections means actually yes, the output admittance is very high, that is low, that is output impedance is very much high with respect to RL, so you can omit this. Okay, you can omit this. Actually this will be acting as 1 by HO is the resistance. You know, HO is the output admittance, so 1 by HO is the output resistance, and output resistance is very large than the load resistance, and that is why this path should be cancelled, because as this path has infinite kind of resistance, very high resistance, so no current should pass along this path, so the model can be simplified by not taking this into the consideration. Similarly, yes, so the equations are very easy here. Now HRE is also a very small term, so you can also neglect the HRE. Okay, it is written here again. So the net connection, see here the HRE is not here, it is 0, and HO is not there. Okay, HOE is not there, so 1 by HO is infinity, means HO is 0. So those are terms which are not included, so the circuit is very much simpler. The black box is now simpler with respect to the previous study, the general study. It is not general, it is special case. So the approximate C hybrid model, it is also important because it has some applications also. So you can see HOE, it is not there, so 0. So HIE, that is current gain, is HFE. And what is HFE here? You can write HFE is the I have at the beginning of my lecture I have told you that HFE is the output current by input current. So output current is the collector current, input current is the base current, so it is nothing but your beta. So beta is actually HFE, and beta actually the current gain for the approximate model of common emitter mode. Similarly, input impedance, those comes very naturally and very easily. All the things, all the values are approximated here, but very useful. Output impedance, it becomes 0, infinity, and it is okay. The approximate models for the yes, it is summarized here. See, you can see the differences of the formula of the approximated model and the actual model of CE mode amplifier, but for same calculations for CC or CB mode are not included in our syllabus, so we should skip it. We should skip those things. Yes, some problems regarding the common emitter amplifier. You can see the values can be given and something will be asked. For this you have to remember the main formula for current gain, voltage gain, input resistance or input admittance, or the output resistance or the output admittance. Those formulas should be remembered, and you can also remember the approximate analysis, and you can see whether the actual results and the approximated results are deviated from each other by doing those two problems. Okay, so here I am closing this session, and I am going to summarize now. And in this class, first we have learned about the hybrid model, why it is called hybrid model, then how the circuit is drawn, and then the three modes CE, CV and CC, and how the hybrid model looks like into those three modes of connections. And now calculation of current gain, voltage gain, input resistance and output resistance, or actually you can say output resistance or the output admittance. And by considering actual source, the current gain is overall current gain replaced by overall current gain, overall voltage gain, overall input and overall output. So those things, and last thing is the approximate model, and this by approximate model because in this model HO is taken as 0 as well as reverse voltage gain is taken as 0. So the circuit will be simpler, and the same quantities are again evaluated using the approximate mode, but using only CE mode. Just consider only one mode. Okay, and numerical problems are here. Those are very important for your exam preparations. So let me thank you for listening.